Something happened in the void beyond Earth's atmosphere that nobody is talking about the way they should. Not a malfunction, not a delay, not the kind of bureaucratic setback that gets buried in a press release and forgotten by Monday morning. What happened during Artemis II cuts deeper than that. It touches something older than space programs, older than rockets, older than the dream of leaving this planet behind. It touches the raw, unfiltered reality of what human flesh actually is when it leaves the only environment that has ever kept it alive. 4 astronauts, 1 capsule, 250,000 miles of absolute nothing between them and the moon. And the universe, for the first time in 50 years, said, "We are taking humans back out there, into the radiation, into the silence, into the pressure differential that would turn an unprotected body into something unrecognizable in under 2 minutes. Back into a place where the sun is not a warm comfort on your face, but a weapon, a particle cannon firing streams of ionizing radiation that slice through metal, through shielding, through human DNA like it was never there." Here is what most people do not understand about the Artemis II mission. The disturbing part is not what went wrong. The disturbing part is how much we already know about what could go wrong, what the numbers say, what the physics demands, and how we chose to go anyway. The disturbing part is that every single calculation NASA ran before clearing those 4 human beings for that trajectory included an accepted margin for biological damage. Not a possibility. An acceptance. That is the sentence that should stop you cold. There is a number, a measurable, documented threshold, beyond which radiation exposure begins to statistically alter the cellular machinery of the human body. Artemis II crossed into territory where that number becomes relevant in ways the Apollo missions only briefly touched. The Van Allen belts, those twin rings of magnetically trapped charged particles wrapping the Earth like invisible armor, do not care about mission timelines. They do not care about launch windows or political deadlines or the weight of national pride. They are ancient. They have been here for billions of years, and every human being on that spacecraft had to pass through them. The shielding on the Orion capsule is real. The engineering is extraordinary. But shielding does not stop radiation. It slows it. It degrades the particle energy. It transforms some of it into secondary radiation, which in certain cases is more biologically damaging than the original beam that struck the hull. This is not speculation. This is the documented physics of particle interaction with dense matter. When a high-energy proton hits aluminum, it does not disappear. It creates a cascade. So when you hear the word disturbing in the title of this story, understand that it is not a metaphor. It is not clickbait. It is the honest word for the feeling you get when you read the biological risk assessments that NASA publishes openly, documents that describe acceptable cancer probability increases in matter-of-fact language, the way an actuary describes the expected lifespan of a bridge. These 4 human beings signed their names to that math, and they went anyway. That is where this story begins. Not with disaster, not with conspiracy, but with the quiet, almost unbearable courage of people who looked at what the universe actually is, read every page of what it will do to a human body, and said yes. And with the equally quiet, equally unbearable question that follows them home. What exactly did they come back carrying? To understand what Artemis II truly means, you have to first understand what the human body is, not what we imagine it to be, not the heroic vessel of poetry and religion, the actual biological object, the 300 trillion cells arranged in a collaboration so ancient and so precise that it took 4 billion years of uninterrupted planetary stability to produce it. Every cell in the human body evolved inside a magnetic shield, inside an atmospheric filter, inside a gravitational constant that shaped the architecture of every bone, every vessel, every organ. The Earth did not simply provide a home for life. The Earth built life in its own image. The oxygen concentration, the pressure at sea level, the specific wavelengths of solar radiation that the ozone layer permits to pass, the gravity that pulls fluid through the lymphatic system, the magnetic field that deflects the most violent particle storms the sun can produce. All of it woven into the biological code of every living thing on this planet over timescales that make human civilization look like a rounding error. When you remove a human being from all of that, something fundamental shifts. It does not shift dramatically at first. It does not announce itself. The astronaut does not step outside the capsule and immediately feel the universe pressing against them. The body is resilient. It compensates. It adjusts. But underneath that surface resilience, at the molecular level, in the nucleus of every dividing cell, the environment of deep space begins to leave its signature immediately. Within hours of leaving Earth's magnetic protection, cosmic rays, those high-energy atomic nuclei accelerated to near light speed by distant supernovae, and the shock fronts of dying stars begin passing through the hull, through the seat, through the suit, and through the soft tissue of the human body without stopping. Think about what a cosmic ray actually is. It is not light. It is not a wave. It is matter, a single iron nucleus, stripped of its electrons, traveling at 99% the speed of light. It carries more kinetic energy in that one particle than you could release by detonating a stick of dynamite focused to a microscopic point. When it enters a human body, it does not stop at the skin. It does not stop at muscle. It passes through everything, and as it does, it ionizes the molecules along its path, tearing electrons away from atoms, breaking chemical bonds, fragmenting the precise molecular geometry that keeps cellular processes functioning. It leaves behind what physicists call a track, a corridor of biological damage so narrow it is invisible, yet so energetically violent that the DNA double helix it intersects does not simply mutate, it shatters. The body has repair mechanisms for this, extraordinarily sophisticated ones. Enzymes that patrol the genome, identify breaks, and stitch the code back together. But those repair mechanisms evolved for the radiation environment of Earth's surface, where cosmic rays are attenuated by the equivalent of 10 meters of water above every square centimeter of your body. In low Earth orbit, the shielding drops. Beyond the Van Allen belts, it essentially disappears. The repair systems are not broken. They are simply overwhelmed by a rate of damage they were never designed to handle continuously. This is not a crisis. This is a calculation. NASA has published, in documents available to anyone willing to read them, something called the Reid value, the risk of exposure-induced death. It is expressed as a percentage. It is calculated per mission. It accounts for the astronaut's age, their sex, their baseline cancer risk, the trajectory of the spacecraft, the duration of exposure, and the current phase of the solar cycle. It is then compared against an acceptable threshold. And that threshold, that number beyond which NASA considers the risk too high to approve a mission, is itself a number that should make you pause. Because it is not zero. It was never zero. The acceptable limit for a career astronaut is a 1 in 6 chance of developing fatal cancer attributable to radiation exposure. 1 in 6. the same odds as a single pull of a trigger in Russian roulette. That comparison is not rhetorical flourish. It is an honest translation of the statistical weight of what those documents contain. The people who designed the Artemis program knew this number before the first bolt was tightened on the first piece of hardware. The astronauts who trained for Artemis II knew this number before they signed their flight assignments. It was not hidden. It was printed in technical language in official reports and placed in filing systems where most people would never look for it and could not interpret it if they did. And yet, here is where the philosophy of this mission becomes genuinely vertiginous. What does it mean for a civilization to decide that a 1 in 6 mortality risk is acceptable in the pursuit of knowledge? Not in war, where the moral calculus has its own brutal logic. Not in emergency response, where the risk is accepted to save another life. In exploration, in the deliberate, planned, voluntary act of sending human beings into an environment that will statistically damage them. Because the alternative, staying home, staying safe, staying inside the magnetic bubble our planet provides, means remaining forever ignorant of something we desperately need to understand. The moon is not simply a destination. The moon is a laboratory. It is the closest body in the solar system where humanity can learn, in real time with real bodies, whether we are capable of surviving beyond this planet. And that question, whether the biological architecture assembled by 4 billion years of terrestrial evolution can be successfully exported to another world, is not an academic question. It is the most consequential question our species has ever asked. Because if the answer is no, or not without radical modification, the implications cascade outward with a force that destabilizes every optimistic narrative about humanity's future. The dreams of Mars colonies, of generation ships, of a multi-planetary civilization spreading across the galaxy, all of them rest on the assumption that the human body, with sufficient engineering support, can endure the journey. Artemis II is the first real stress test of that assumption since Apollo 17 left the lunar surface in December of 1972. More than 50 years of silence. More than 50 years during which our understanding of radiation biology, of galactic cosmic ray flux, of the long-term neurological effects of microgravity, of the immunological suppression that begins within days of leaving Earth's gravity well, has deepened enormously. And what that deepening has revealed is not reassuring. It is a portrait of a body that is profoundly, exquisitely, almost heartbreakingly dependent on the specific conditions of its home planet. The spine lengthens in microgravity as the intervertebral discs, no longer compressed by the weight they evolved to bear, expand with fluid. This sounds benign. It is not. The expansion stretches the spinal cord. It increases the risk of herniation. It changes the geometry of the neural pathways that carry sensation and motor signals to every part of the body. Astronauts return from long-duration missions measurably taller and in significant pain that can persist for months. The visual system is equally compromised. Intracranial pressure rises in microgravity because the fluid that cushions the brain redistributes toward the head without gravity to pull it downward. That pressure presses against the optic nerve, flattening the back of the eyeball, shifting the focal point, permanently altering the vision of astronauts who spend long periods in space. These are not fringe observations. They are documented in the longitudinal studies of astronauts returning from the International Space Station. They are the baseline against which the Artemis II astronauts were measured before, during, and after their mission. Every change in their physiology, every shift in their blood chemistry, every subtle alteration in the fluid dynamics of their central nervous system became data. they did not simply travel to the moon and back. They submitted their bodies as instruments of measurement, as biological sensors in an experiment whose full results will take years to analyze. There is something almost sacred about that, and something almost terrifying. Because the data they are generating is not just about them, it is about all of us. It is about the biological feasibility of the future we are trying to build. Every anomalous reading in their post-flight medical examinations, every unexpected cellular marker in their blood work, every documented change in their cognitive performance, narrows or widens the corridor through which the human species must pass if it is ever going to leave this planet permanently. The astronauts of Artemis II became, in the most literal sense, the edge of the human experiment. And the universe does not run experiments gently. Consider the timing. The Artemis II mission flew during a period of elevated solar activity. The Sun, following its approximately 11-year cycle, was approaching and crossing solar maximum, the peak of its magnetic activity cycle, during which sunspot counts rise. Coronal mass ejections become more frequent, and the probability of a significant solar particle event, a sudden burst of high-energy protons erupting from the solar surface at a significant fraction of the speed of light, increases dramatically. A major solar particle event, if it occurred during a deep space mission with no Earth magnetic field for protection and no immediate shelter capable of blocking the particle flux, would deliver a radiation dose that could be acutely dangerous within hours. Not over a career, not statistically distributed across decades. Acutely. The nausea would begin first, then the fatigue, then, depending on the dose, the deeper symptoms of acute radiation syndrome that the body cannot simply compensate its way through. The mission architects knew this. They built response protocols. They identified the densest section of the Orion capsule, packed with water and equipment, where the crew could shelter if solar monitors detected an incoming event. The plan existed. The contingency was real. But a plan is not a guarantee. It is a probability adjustment. And in the mathematics of deep space, probability adjustments are the only currency available. The disturbing truth about Artemis II is not that something catastrophic occurred. The disturbing truth is how precisely, how scientifically, how thoroughly we have mapped the ways in which it could have. And how that map, drawn in the clean language of physics and biology, describes a journey that human bodies were never designed to take. We took it anyway. That fact deserves more than a headline. It deserves to be held still, in silence, and examined from every angle. Because what it reveals about the human species is not simply bravery. It is something stranger and more complex than bravery. It is the willingness to look directly at the mechanism of our own potential destruction, understand it completely, and then step forward into it. Not because we do not know what it will cost, but because we have decided that the cost of not knowing is higher. That is the calculation underneath Artemis II. And it is one that every generation from this point forward will have to make again, with higher stakes, across greater distances, in environments that make the cislunar space of this mission look like a gentle warm-up for what comes next. There is an ocean surrounding this planet that you cannot see, cannot feel, and cannot escape. It has no surface. It has no floor. It is not made of water or air or any substance that the human senses were designed to detect. It is made of magnetism and motion, of charged particles spiraling along invisible field lines that arc from pole to pole, looping through space in elegant curves that a physicist can calculate to extraordinary precision and that a human body can cross in complete, total ignorance of the forces reshaping it at the atomic level. This is the magnetosphere, and it is, without exaggeration, the reason you are alive. Not in the abstract philosophical sense. In the precise, mechanistic, molecular sense. The solar wind, that continuous stream of plasma erupting from the sun's corona and expanding outward at speeds between 300 and 800 kilometers per second, carries with it a magnetic field, a churning, variable, occasionally violent extension of the sun's own magnetic personality. Without a planetary shield to deflect it, that wind would not simply blow past the Earth. It would strip the atmosphere. Over millions of years, it would peel away the gases that moderate temperature, filter ultraviolet radiation, and carry the oxygen that every aerobic organism on this planet depends upon to power its cellular machinery. We know this is not a theoretical concern because we have a neighbor that demonstrates the outcome in real time. Mars, a world that once had a magnetic field, once had a thick atmosphere, once had liquid water flowing across its surface in volumes that carved canyon systems visible from orbit, lost its internal dynamo approximately 4 billion years ago. Without the magnetic shield, the solar wind began its work. The atmosphere thinned, the water sublimated or froze into the subsurface. The surface became a freeze-dried, radiation-bathed, oxidized desert, where the ultraviolet flux at ground level is sufficient to fragment organic molecules on contact. Mars is what Earth looks like after the magnetosphere fails. It is a warning written in geology, preserved in the rock record, readable by any civilization sophisticated enough to send instruments there to measure it. We are that civilization. We sent those instruments. We read that warning, and then we designed a mission that deliberately carried 4 human beings beyond the protection of the very shield whose absence turned our neighboring planet into a wasteland. Let that sequence of events sit with you for a moment. The Van Allen radiation belts are the innermost, most concentrated expression of the magnetosphere's particle-trapping power, named for the physicist James Van Allen, who confirmed their existence with instruments aboard the first successful American satellite in 1958. They consist of 2 primary regions of space, where the geomagnetic field captures and holds charged particles in spiraling trajectories, bouncing them back and forth between the magnetic poles in a continuous, energetic dance that has been ongoing for as long as Earth has had a magnetic field. The inner belt, beginning roughly 1,000 kilometers above the surface and extending to about 13,000 kilometers, is dominated by high-energy protons. These are not gentle particles. A proton traveling at a significant fraction of the speed of light carries enough energy to penetrate several centimeters of aluminum before losing enough momentum to stop. The Orion capsule's hull is not several centimeters of solid aluminum. It is an engineered structure, optimized for weight, thermal performance, and structural integrity, which means the shielding it provides against high-energy protons in the inner belt is real but finite, a calculated reduction rather than an elimination. The outer belt, extending from roughly 13,000 to 60,000 kilometers altitude, is dominated by highly energetic electrons. These particles present a different kind of challenge. Electrons, when decelerated by shielding material, produce Bremsstrahlung radiation, a German word meaning breaking radiation, which describes the X-ray photons emitted when a charged particle is suddenly slowed. So the act of shielding against electrons can, under the wrong conditions, produce a secondary radiation field of penetrating X-rays inside the very structure designed to protect the crew. The engineers who designed Orion's radiation shielding spent years modeling this cascade effect. selecting materials and geometries that minimize secondary production while still reducing primary particle flux. The result is a compromise. All engineering is compromise. In radiation shielding for human spaceflight, the compromise is expressed in millisieverts and probability distributions. The Apollo mission solved the Van Allen belt problem with speed. The Saturn V upper stage and the Apollo spacecraft flew a trajectory that minimized time in the highest flux regions of the belts, passing through the most dangerous zones in a matter of hours rather than days. Orion, on the Artemis II trajectory, faced the same challenge with a different vehicle, different trajectory constraints, and a scientific community that now knows considerably more about what those hours of exposure actually do to human tissue than the flight surgeons of 1969 understood. What they know is this: it is not simply the total dose that matters. It is the dose rate, the type of radiation, the specific tissues exposed, and the biological state of the individual receiving it. A given quantity of ionizing radiation delivered rapidly is more damaging than the same quantity delivered slowly, because the rapid delivery overwhelms the repair mechanisms before they can respond. High-energy heavy ions, the iron nuclei and silicon nuclei that make up a portion of the galactic cosmic ray spectrum, are disproportionately damaging relative to their contribution to total dose, because they produce dense ionization tracks that are extremely difficult for cellular repair enzymes to reconstruct accurately. And here is the detail that tends to disappear in the broad strokes of public science communication. The brain is not exempt. For decades, the primary concern in astronaut radiation health focused on cancer risk, on the statistical elevation of malignancies across various organ systems that accumulates over a career of spaceflight. But research conducted over the past 15 years, much of it using rodent models exposed to simulated galactic cosmic ray spectra at facilities like the NASA Space Radiation Laboratory at Brookhaven, has revealed something that the cancer-centric framework entirely missed. Cosmic radiation causes neurological damage. Not in the distant future, not as a statistical ghost haunting decades later medical records, but in the structure and function of the central nervous system, in ways that manifest as measurable cognitive changes within months of exposure. The specific mechanism involves the hippocampus, the seahorse-shaped bilateral structure deep in the temporal lobe that is central to the formation of new memories, to spatial navigation, to the contextual processing of fear and anxiety. Neurons in the hippocampus are among the most sensitive in the central nervous system to ionizing radiation. They do not divide rapidly. They do not replace themselves easily. When a high-energy iron nucleus tracks through the hippocampal tissue of an astronaut during a transit to the moon, the damage it leaves is not repaired on the timescale of a mission. It persists, and the cumulative effect of thousands of such events across the duration of a deep space journey is not theoretical. It has been documented in animal studies with a consistency that has moved it from a speculative concern to a recognized risk in NASA's long-duration mission planning. The astronauts of Artemis II were not on a long-duration mission. Their trajectory carried them around the moon and back, a journey measured in days, not months. But every day beyond the magnetosphere is a day in which the galactic cosmic ray environment operates on the brain without attenuation. Every hour in the Van Allen belts is an hour of elevated proton flux penetrating the skull. The cerebrospinal fluid, the delicate architecture of the cerebral cortex. The dose is real. The biological response is real. The long-term significance of that response for those 4 specific individuals will only be known across the arc of their remaining lives. measured in the careful neurological follow-up that post-flight medical protocols require. They became, in this sense, longitudinal subjects of their own experiment. Their futures carry embedded within them data that the rest of us need. This is the exchange that deep space exploration demands. Not simply risk, not simply courage. A specific, informed, voluntary surrender of biological certainty in exchange for knowledge that cannot be obtained any other way. There is no simulation that replicates the actual galactic cosmic ray spectrum at lunar distance. There is no ground-based facility that can expose human subjects to the full energetic range of particles encountered beyond the magnetosphere. The only way to know what happens to human beings in deep space is to send human beings into deep space and measure what happens to them. Artemis II is, in this clinical sense, a human experiment. The most carefully designed, most ethically scrutinized, most technologically supported human experiment in the history of spaceflight, but a human experiment nonetheless. And the ethics of that designation carry weight that tends to get lost in the celebrations of launch day and the relief of splashdown. Because there is a tradition in the history of science of experiments whose full implications were not understood until long after the results were in. A tradition of moments when the boundary between knowledge and harm was crossed before anyone realized exactly where that boundary lay. Medicine is full of these moments. Physics is full of them. The history of radiation science itself is written partly in the bodies of the pioneers who worked with radioactive materials before the biological consequences were understood, whose names are attached to fundamental discoveries and whose medical records are attached to the early documentation of radiation-induced malignancy. We are not in that position of ignorance with Artemis II. We know what radiation does. We know what microgravity does. We know the mechanisms. We know the dose rates. We know the repair kinetics. We know the probability distributions. The knowledge is there, detailed and documented, published in peer-reviewed literature and translated into mission planning documents. What we do not know, what no amount of prior knowledge can fully specify in advance, is the individual response. The 4 astronauts who flew Artemis II are not average cases drawn from a statistical distribution. They are specific people with specific genomes, specific baseline health profiles, specific epigenetic histories, specific repair enzyme efficiencies that differ from each other in ways that are biologically significant but practically unmeasurable in advance. The population-level risk estimates tell us what happens to 1,000 people exposed to this environment. They do not tell us, with precision, what happens to these 4 people. That irreducible uncertainty is the deepest layer of the disturbing reality at the heart of this mission. We can calculate, we can model, we can optimize. We can reduce the probability of harm to the lowest value that engineering and trajectory design and mission duration allow. And then, at the end of all that calculation, 4 human beings still have to climb into the capsule and trust the math in ways that the math itself cannot fully justify. Because the math deals in populations and the capsule contains individuals. And the gap between those 2 things, the unbridgeable distance between the statistical and the personal, is where the full weight of what Artemis II actually means comes to rest. Out there, beyond the invisible ocean that has kept us alive since before our species had a name for the sky. The universe operates according to rules that did not write themselves with human survival in mind. The galactic cosmic ray environment exists because stars explode. Because the remnants of those explosions accelerate particles across interstellar distances over timescales that dwarf the entire history of life on Earth. The solar wind exists because fusion reactions in the core of a middle-aged star produce energy that must eventually escape. And it escapes in every direction simultaneously, indifferent to the small blue world orbiting at one astronomical unit. These are not hostile forces. Hostility requires intention. What makes deep space genuinely, philosophically disturbing is precisely the absence of intention. The radiation that passed through the bodies of the Artemis II crew did not target them. It did not know they were there. It has been passing through that region of space since long before the solar system formed, since long before there was a sun to orbit, since the galaxy itself was young and its population of massive, short-lived stars was exploding at a rate that would be unrecognizable to the astronomers of today. The astronauts flew through something ancient and vast and entirely indifferent, and they came back carrying traces of it in their cells. That is not metaphor. That is biology. That is the literal, measurable, documented reality of what Artemis II put into the world. There is a number that does not appear in press releases. It does not feature in the highlight reels of launch day coverage or in the carefully composed statements that public affairs offices release to a waiting world. It is not classified. It is not hidden. It lives in the technical documentation of deep space communication systems, in the frequency planning charts and signal propagation models that mission controllers rely on every second of every hour that a crew is beyond low Earth orbit. The number is this. At lunar distance, a radio signal traveling at the speed of light takes approximately 1.3 seconds to make the one-way journey between the Orion capsule and the antennas of the deep space network on Earth. 1.3 seconds in each direction. A round-trip communication delay of approximately 2.6 seconds minimum. That delay is not a technical inconvenience. It is a philosophical statement about the nature of the mission. It means that in any emergency developing faster than that round-trip window, the crew is alone. Not metaphorically alone. Not psychologically alone in the way that a soldier in a remote posting might feel isolated from command. Physically, informationally, causally alone. The speed of light itself becomes the wall between the astronaut and the institution that trained them, equipped them, and is monitoring their every vital sign from the comfort of a climate-controlled room in Houston. Think about what that means in practice. Imagine a pressure anomaly developing in a spacecraft system. Imagine the first sensor reading that flags the anomaly appearing on the crew's displays at exactly the same moment it appears on the consoles in Mission Control. The crew sees it. Mission Control sees it. But the crew's response, their voice report, their request for guidance, takes 1.3 seconds to arrive in Houston. The flight controller's analysis and recommended action takes another 1.3 seconds to return. In those 2.6 seconds, the anomaly has continued developing. The crew has had to begin acting on their own judgment before the round-trip conversation is even complete. This is not a flaw in the mission design. It is an inescapable consequence of operating at the distances that the solar system demands. And it is a preview, a mild, almost gentle preview, of what communication delays will mean for missions to Mars, where the one-way signal travel time ranges from 3 minutes to 22 minutes, depending on orbital geometry. At Mars, Mission Control does not advise in real time. It cannot. The crew is not extended by an institution. They are a self-contained decision-making system, carrying within the boundary of their own capsule all the knowledge and judgment that must substitute for the entire engineering organization behind them. Artemis II was, in this sense, a rehearsal for a kind of human autonomy that our civilization has not required since the age of ocean exploration, since the era when a ship departing from a European harbor crossed beyond the horizon and entered a communicative silence that would not break until it returned. Or did not return, months or years later. The captains of those vessels carried in their heads and in their sealed orders everything their civilization knew about navigation, weather, disease, conflict, and survival. They made decisions that could not be reviewed, could not be appealed, could not be second-guessed in real time by anyone with more information or greater authority. The Artemis II crew carried something analogous. Not sealed paper orders, but years of training compressed into procedural memory, into the kind of deep expertise that does not require conscious retrieval because it has been practiced until it becomes reflex. Every system on the Orion capsule, every failure mode, every emergency response, every contingency that mission planners could imagine and script and simulate, lived in the minds and muscle memory of those 4 people, in a way that no amount of real-time ground support could replicate or replace. But there is a limit to what training can anticipate. And in the silence between signals, that limit becomes the frontier. The psychological dimensions of that silence are documented with increasing precision in the research literature on isolated and confined environments, studies conducted in Antarctic winter overstations, in submarine deployments, in the Mars 500 isolation simulation that confined 6 volunteers in a Moscow facility for 520 days in a mock interplanetary mission, converge on a consistent portrait of what happens to human cognition and emotional regulation when communication with the outside world becomes delayed, reduced, and eventually nearly meaningless. The third quarter effect is one of the most reliably documented phenomena in this literature. In isolated missions of defined duration, performance and morale tend to dip most severely not at the midpoint, but approximately 3/4 of the way through. When the end is visible enough to create longing, but distant enough to remain unreachable. Interpersonal friction increases. Sleep quality degrades. Risk assessment shifts in subtle ways that are difficult to quantify, but consistently observable. The confined environment, no matter how intelligently designed, begins to accumulate a psychological weight that training can mitigate but cannot eliminate. For Artemis II, with its relatively short duration compared to a Mars mission, the third quarter effect was not the primary psychological concern. The primary concern was something more immediate and perhaps more primal: the overview effect and its psychological inverse. The overview effect is the term coined to describe the cognitive and emotional shift reported by astronauts who see the Earth from space. The sudden, visceral comprehension of the planet's fragility, its isolation, its breathtaking beauty against the absolute black of the surrounding void, produces in many astronauts a transformation in perspective that they describe as permanent, as a reorganization of values and priorities that does not fade upon return to the surface. It is documented across decades of astronaut testimony, across national boundaries and ideological differences, with a consistency that suggests it is not a cultural response, but a neurological one, a specific reaction of the human visual and cognitive system to a stimulus it was never designed to process. But the Artemis II crew flew further than the overview effect's classical setting. They flew to a distance where the Earth itself, the entire planet, could be covered by an outstretched thumb, where the object that contains every human being who has ever lived, every city, every ocean, every mountain range, every ecosystem, every accumulation of meaning and history that the word home carries, becomes a small blue disk hanging in an immensity that does not acknowledge its existence. The psychological inverse of the overview effect has no universally accepted name yet, but the phenomenon it describes has been reported by lunar astronauts with a consistency parallel to the overview effect's documentation. It is not simply loneliness. It is a specific kind of cognitive disorientation that arises from the direct perception of scale that the human nervous system has no evolutionary context for processing. The brain did not develop in an environment where the horizon could be the edge of the visible universe. It developed in environments bounded by geography, by atmosphere, by the comfortable limits of the biosphere that kept its ancestors alive. To suddenly perceive those limits from outside them, to look back at them from a distance where they are no longer perceptible as limits, but as a single small point of concentrated existence, is to experience something for which no psychological framework fully prepares you. Some Apollo astronauts described a quiet that was different from any quiet on Earth. Not simply the absence of sound, which is expected in the vacuum of space. A quality of silence that was not sensory but existential. A silence that came from being in a place where nothing in the surrounding environment had any relationship to human presence. Not hostile, not welcoming. Simply indifferent on a scale that made the concept of indifference feel inadequate. The Artemis II crew experienced this. They carried it. They brought it back, folded into their post-flight debriefs and their medical evaluations, and the quiet pauses in interviews where the question was about what it felt like, and the answer took a moment longer to arrive than the interviewer expected. That pause is data too. Not the kind that fits in a spreadsheet, but data nonetheless, and it points towards something that the technical risk assessments, for all their rigor and detail, do not fully capture. There is a dimension to deep space that is not physical and not purely psychological, but something that sits at the intersection of both. Something that has to do with the specific human experience of confronting a reality that does not include you, that has no record of your existence and would register no change at your absence. The universe is approximately 13.8 billion years old. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. The observable universe contains more galaxies than there are grains of sand on every beach and desert on Earth. And in this particular corner of one spiral arm of one of those hundreds of billions of galaxies, 4 human beings climbed into a metal capsule and flew to a rock orbiting a medium-sized star, and then came home. The cosmic insignificance of that act is absolute. The human significance of it is equally absolute. Both things are true simultaneously, and the tension between them does not resolve. It simply persists, like a chord struck on an instrument and never released, vibrating in the background of everything that the Artemis program means and everything that it is trying to become. The silence between signals is where that tension lives most purely. In those 1.3 seconds when the voice of a crew member is traveling across 250,000 miles of vacuum toward an antenna on a planet they can cover with their thumb. In those 1.3 seconds of the return signal, carrying the voice of a flight controller who is sitting in a building on a surface that everything in the human species evolved to regard as the ground, the foundation, the unchallengeable baseline of reality. The signal travels, the silence holds it. And in that silence, the distance between what we are and where we are trying to go is briefly, nakedly visible. That distance is not measured in miles. Miles are manageable. Miles are a unit of engineering. The distance that the silence reveals is measured in the gap between a nervous system designed for the African savanna and an environment defined by the physics of stellar explosions and the geometry of orbital mechanics. It is the distance between the animal that learned to use fire and the civilization that learned to build spacecraft, between the cognitive architecture assembled by natural selection across millions of years and the intellectual ambition assembled by culture across a few thousand. That gap is what every deep space mission crosses. Not the 250,000 miles to the moon. Not even the 140 million miles to Mars. The gap between what biology made us and what we are determined to become. And it is a gap that no amount of training, no thickness of shielding, no sophistication of life support engineering can entirely bridge. It can be narrowed. It has been narrowed, mission by mission, decade by decade, measurement by measurement. But it remains. It persists in the specific vulnerability of the human body to the radiation environment of deep space. It persists in the communication delays that make true real-time collaboration with Earth impossible beyond certain distances. It persists in the psychological weight of the overview effect's inverse, in the existential vertigo of perceiving scale that evolution never prepared us to perceive. Artemis II flew across that gap, 4 people in a capsule, carrying the accumulated engineering of a civilization, and also carrying within their own bodies the irreducible, unmodifiable, 4-billion-year-old biological inheritance of a species that came from the surface of a protected, temperate, magnetically shielded world. They crossed the gap. They came back. But the gap did not close behind them. It simply became more precisely mapped. And a more precisely mapped gap is both more manageable and more confronting than an unknown one. Because once you know exactly where the boundary lies, you cannot pretend it does not exist. You cannot plan around it as though engineering alone will eventually make it irrelevant. You have to look at it directly, with all the clarity that measurement provides, and decide what you are willing to accept in order to cross it again. That decision is not made once. It is made before every mission. It will be made before every mission to follow. It is the permanent, recurring, unavoidable moral question at the center of human spaceflight. And Artemis II did not answer it. It sharpened it. It made it more specific, more informed, more grounded in data than it has ever been before. Which means the next time the question is asked, it will be asked with less ignorance and no less weight. The silence between signals carries all of this. Every launch, every transit, every orbit, every re-entry. It carries the data and the courage and the biological cost and the philosophical vertigo and the irreducible uncertainty that no calculation can eliminate. It carries 4 people in a capsule at the edge of everything their species has ever been, asking without words whether what lies beyond is worth what it takes to reach it. The moon has no atmosphere. This fact is stated so routinely, absorbed so casually into the background knowledge of anyone who has passed through a basic science education, that its full weight almost never lands. It is treated as a simple physical characteristic, like the color of a mineral or the boiling point of a compound, a property, a data point, something to note and move past on the way to more dramatic information. But stop, then stay with it. Let it expand into what it actually means. No atmosphere means no wind, no weather, no erosion in the conventional sense, no sound, no medium through which pressure waves can propagate, which means that on the lunar surface, an explosion occurring 10 meters from you would be completely inaudible. The shock wave would travel through the regolith, through the soles of your boots, into your feet and legs and spine as vibration. But the air that your ears evolved to detect pressure variations in does not exist. The moon is a place where violence is silent, where destruction announces itself only through the ground beneath you and the light in front of you, and never, ever through sound. This is not a minor sensory curiosity. It is a fundamental reorganization of the relationship between cause and effect as a human being experiences it. sound is warning. Sound is the component of the environment that carries information about events happening outside the field of vision, behind you, around corners, beyond obstacles. The rustle that preceded the predator. The crack that preceded the falling branch. The low rumble that preceded the flood. Human neurology is wired at a depth below conscious thought to treat sound as the primary carrier of threat information from the surrounding environment. On the lunar surface, that entire sensory channel is severed. The psychological implications of this have been studied in the context of extravehicular activity planning, in the design of suit-based vibration alert systems that attempt to partially substitute tactile sensation for absent auditory warning. But no engineering solution fully replaces what evolution spent millions of years building. The suited astronaut on the lunar surface moves through a silence so absolute that it has a texture, a presence, a quality that former moonwalkers have described with a consistency that makes it one of the most reliably documented sensory experiences of spaceflight. It is not peaceful. Peaceful implies the absence of something that was present. This is different. This is the presence of something, a quality of environment that has no analog in any human sensory experience accumulated on the surface of the Earth. And beneath that silence, the ground itself is treacherous in ways that are only now being fully appreciated. Lunar regolith, the layer of fragmented rock and dust that covers the moon's surface to depths ranging from a few meters to tens of meters, is not like terrestrial soil. It has never been weathered by water. It has never been processed by biological activity. It has never been rounded by the friction of particles moving against each other in fluid. Every grain, every fragment, is the direct product of impact events and thermal cycling and micrometeorite bombardment operating over billions of years in a vacuum. And the result is a material whose particles are sharp-edged, irregular, electrostatically charged, and extraordinarily fine in ways that make it unlike anything the human respiratory system or the mechanical systems of spacecraft have encountered in their operational histories. The Apollo astronauts brought lunar dust back with them. Not intentionally, not as samples in sealed containers, but on their suits, on their equipment, on the surfaces of everything that had contact with the lunar surface. And once inside the capsule, that dust became a problem that nobody had fully anticipated. It was abrasive beyond the expectation of the engineers who designed the suit seals and connectors. It clung to surfaces with an electrostatic tenacity that made it nearly impossible to brush away. And when the astronauts removed their helmets inside the pressurized module and inhaled the cabin air, they smelled it. They described the smell of lunar dust as similar to spent gunpowder. Sharp, acrid, immediately recognizable as something foreign to any terrestrial environment. That smell is the olfactory detection of reactive mineral surfaces that have never been exposed to an oxidizing atmosphere. Surfaces that carry chemical reactivity built up over billions of years of vacuum storage, suddenly encountering the oxygen and moisture of human breath and beginning to react. The toxicological implications of that reactivity are still being studied. Freshly fractured silicate minerals are known to generate reactive oxygen species on their surfaces, compounds that in sufficient quantity can initiate inflammatory responses in lung tissue. The specific chemistry of lunar dust reactivity in a biological environment is one of the active research areas informing Artemis mission planning. Because unlike the brief surface excursions of Apollo, the long-duration lunar surface stays planned for later. Artemis missions will involve repeated, extended exposure to the dust environment in ways that could accumulate biological consequences over timescales that Apollo never approached. Artemis II did not land on the lunar surface. Its trajectory was a free return flyby, a path that carried the crew around the moon without entering lunar orbit and without any surface operations. But the mission's relevance to surface operations is direct and causal. It is the human validation of the systems and procedures and physiological baselines that will support the astronauts who will land. Every data point gathered from the Artemis II crew, every measurement of their physiological response to deep space radiation and microgravity and psychological isolation, becomes an input to the risk models for the surface missions that follow. Which means Artemis II carries in its data the lives of people who are not on it. That is a form of responsibility that does not get discussed in the language of mission objectives and technical milestones. The crew of Artemis II accepted personal risk in order to generate information that will reduce the risk for crews who come after them. They flew as scouts in the oldest sense of the word, not simply to see what was ahead,